Right, this is the fourth video in the probability section. It's on conditional probability as really quite a sort of interesting topic. Can be a little bit difficult to get your brain around, but I think once you've done that, it kind of opens up quite a lot of potential questions and marks. Okay, so let's just have a look at this question just to kind of illustrate what we are talking about. Okay, so this first part of the question isn't really conditional probability; it just kind of sets the scene. But Xavier, Yuri, and Zara attend a sports center for their judo club's practice sessions. The probabilities of them arriving late are independently 0.3, 0.4, and 0.2, respectively, independently. Whether they arrive late is nothing to do with each other. They travel separately and so on. Calculate the probability that for a particular practice session, all three arrive late. Okay, so because it's independent, then we can multiply these three probabilities together, 0.3 times 0.4 times 0.2, and that's the answer to number one. I'm not even written out because it's not really the gist of this. But none of the three arrives late. Well, that's the probability of them not arriving late is 1 minus this probability. So for Xavier, Yuri, and Zara, respectively, it's 0.7, 0.6, and 0.8. So if we multiply those three together, and then that will give us the answer to part 2. And then only Zara arrives late. So in which case, what we're interested in is the 0.7 for Xavier not arriving late, 0.6 for Yuri, and 0.2 for Zara. So multiply those three together, and we get the solution to part 3. Anyway, on to part B. Zara's friend Wee also attends the club's practice sessions. The probability that Wee arrives late is 0.9 when Zara arrives late and 0.25 when Zara does not arrive late. Now, this is they probably travel together sometimes or something, or they get the same bus from the other corner of town, which may or may not be late, and so whatever. But their lateness is dependent. It's not independent. It's dependent on each other. So what we're saying here is the probability that Wee arrives late is 0.9 when Zara arrives late. So what we're kind of sort of saying is that if we know that Zara is late, or the terminology we might use is given that we know Zara is late, then the probability that Wee is late is 0.9. So that is an expression of a conditional probability. Okay, and 0.25 when Zara does not arrive late. So given that Zara is not late, then the probability that Wee is late is 0.25. Okay, so and then it asks us first calculate the probability that for a particular practice session both Zara and Wee arrive late. Okay, all right, so if we look at our probability tree, and going back to what we did in the previous video, we adopting here the sort of set theory notation. W is the event that Wee arrives late. W prime is the converse. We often use that in sets and probabilities. So that's the probability that Wee is not late, and then same with Z and Z prime for Zara. So let's look at the probability tree for this. We've got from this first node, we've got these two probabilities. Zara being late. I mean, this is given to us in the first part of the question, and Zara not late, 0.8, and these two add up to 1. All the events from a node will add up to 1, probabilities of them. Then we've got the probability that Wee is late given that Zara is late. And this was the notation and nomenclature that sort of I introduced in the previous video. So the probability that we arrives late, given that Zara is late, is this 0.9. So sometimes you have to kind of sort of interpret the conditionality in the statement. The probability that we arrives late is 0.9 when Zara arrives late. So that's a probability that we arrives late given that Zara is late. That's what we're getting at. Okay, so that's 0.9. And the probability that we is not late given that Zara is late is there 0.1. These are two, therefore adding up to 1. And then we've got the when Zara is not late, probability that we is late, even if Zara's on time, is 0.25, and then that's the complement of that we not late, given that Zara not late, 0.75. So we've got all our bits, and we've got all our branches. So we can multiply these together to give us our leaves. And the leaf is the intersection of these two things. That's we being late and Zara being late. So if we multiply these two together, 0.2 times 0.9, 0.18, and so on and so forth, and can work our way down the probability tree. And if we add all those up, we get 1.00. So that means we've multiplied correctly. Okay, so that is what we do there. So just to come back to this, probability of Z times the probability of W given Z is equal to the probability of W intersection Z. Or we might, usually we write it the other way around, actually. The probability of W given Z times the probability of Z is equal to the probability of the intersection of W and Z. So, okay, that's our tree. And then we can answer the questions both. What's the probability that Zara and we both arrive late? Well, that's just this top one, isn't it? There we go, 0.18. And either Zara or we, but not both arrives late. Well, that would be, this one here is Zara, but not we, and this we, not Zara. So it's these two, isn't it? And of course, they're mutually exclusive. We can add these together. And that gives us 0.22. That's the answer to the second part of the question. So that is the use of probability trees for conditional probability. And I think hopefully you agree that actually by using this notation here, it's kind of starts to become a bit more intuitive. Anyway, kind of hold that thought because we'll be coming back to that. So that is a conditional probability, right? Okay. Now, when I mentioned before about probability of, just go back to this, probability of we given Zara times the probability of Zara, if you like, that's what we've got there. Okay. And this little expression here is a form of something called Bayes' rule, sometimes called Bayes' theorem or Bayes' formula, more or less the same things. And that's what we've done there. So you can imagine this on your probability tree. As I say, it's normally written this way around, which is kind of the opposite way around to the branches on your tree, but it's all the same. And we should note also that, of course, it's also true the other way around. If we had these, that would be equal to the intersection. So the consequence of that is this is equal to that. Now, this is useful because this gives us a way of turning around the conditionality. We've got probability that we'll be late depending on Zara, but now if we wanted to reverse the logic and say what's the probability of Zara being late given that we is late, then this actually gives us the ability to do that. Now, if we rewrite that equals that and just divide through by the probability of we being late. That's what we get here, which is again another form of Bayes' rule. The only thing is we often don't actually know this, so we have to decompose this into different parts. So the different possibilities for the probability of W are, first of all, in this case, there are only two on this denominator. The probability of we being late given that Zara is late times the probability of Zara is late, plus the probability that we is late given Zara is not late, times the probability that Zara is not late. So this of course is the same as what we have on the numerator, so that gives us kind of a bit of a hint as to when we're writing this out. We've only got two here, but in other circumstances there may well be more things on the denominator depending on how many different conditions there are attached to, well, in this case, Zara. Zara is not late. Zara's very late. Zara didn't turn up at, or whatever. So, but here we've just got these two, and we can work out what these two are. So now let's just plug the numbers in. We've got all these bits here. So let's have a go. So the probability that Zara is late given we is late is equal to let's have a look at the probability tree that we used. That's 0.9 times the 0.2 there, isn't it? And then on the denominator, we've got that same thing again here. And then we've got the probability that we is late given that Zara is not late. That's that 0.25. It just comes from the question above. And then the probability that Zara is not late is the 0.8, because that's the 1 minus the 0.2 right at the start of the question. So if we just multiply those things through, then we get this 0.18 divided by 0.38, which is 0.77423 decimal places. So that is the probability that Zara is late given that we is late. So that's basically turned, inverted the conditionality, and that's something that does come up. Okay, so right, I think perhaps just we'll have a look at this one, and that will do us here for this section. A patient goes to see a doctor. The doctor performs a test with 99% reliability. That is, 99% of people who are sick test positive, and 99% of the healthy people test negative. Okay, it's good. The doctor knows that only 1% of the people in the country are sick. Okay, that would be called, I think, the prevalence of the disease. So we've got the reliability of the test and the prevalence of the disease. Now the question is, if the patient tests positive, what are the chances the patient is sick? So here we've got the conditional probabilities given to us for like the probability that they're positive, given that they're sick. What this is saying in the final sentence is, if the patient tests positive, what are the chances the patient is sick? So what we want is the probability of sick given test is positive. Right. So this is another one where we're inverting the conditionality. Okay, so if we just apply this into a probability tree, then well, probability that they're sick and not sick, well, that's 1%. So this is the prevalence, I think is the right term, of the disease. Then probability that they're positive given that they're sick is 0.99. That's the reliability of the test. And of course, this therefore must be 0.01, probability negative if they're sick. And then we've got a similar thing here down with these two branches. The probability that they're positive and they're not sick is this 0.01. But the positive probability that they're negative given that they're not sick is 0.99. So again, that's what this is. So we can multiply these through, get the intersections of these two events, and this is what we've got. 0.0099 for sick and positive. Okay, which is not actually what this question is asking. I've underlined that because that's just a question that could be asked. So yeah, all these add up to 1. Again, that's good. So let's just have a look at Bayes' rule again. So the probability that they're sick, given that they've tested positive, right? This is what we're trying to find out, isn't it? That's what the question says. Times the probability of positive is equal to this intersection, but it's also equal to the the other statement with the conditionality reversed. And therefore, we've got the probability that they're sick, given that they're positive, is equal to this numerator here, which I've rewritten there, divided by the probability that the test is positive. Now we've had to kind of divide this up into the 2 cases, because we don't know the probability of them being positive as one single number, but we do know it as the 2 possible cases. So the probability of them being positive given that they're sick times the probability that they're sick, plus the probability that they're positive given that they're not sick times the probability that they're not sick. Okay, so recall that this here, this first one on the denominator is the same as the numerator, and then we just got the other case again. In this situation, we've just got those 2 cases. Okay, so we have therefore, well, what we got? This is 0.99. It's in the question up there. Yeah. Times the probability that they're sick. It's just 1% of the country that's sick. So we've got 0.99 times 0.01. And on the denominator, we've got, well, the same thing again. That's the 0.99 times the 0.01. And then the probability that they're positive, given that they're not sick, well, that is the complement, isn't it? That's the sort of the other side of the reliability statistic. That's the 0.01 times the probability that they're not sick. Well, probability they're not sick, of course, is 0.99. It's only 1% of the population are sick. So we've got this, and we've got the 2 terms on the denominator are actually the same on this particular example. So we can work that through quite easily, and that gives us 0.5. So so you can see that, you know, if you're tested positive for a rare disease, then all is not lost, because you know, the reliability of the test might come and save you. You know, in other situations, 1% actually quite high, really. You know, a lot of these things relate to prevalence of disease, which is much lower than 1%. So find that this figure comes down accordingly. So okay, so that basically is quite a nice example, I think, and perhaps a slightly surprising result. And perhaps a little bit of comfort if you do test positive for a rare disease. Okay, so that the moment is all I think we need to do on conditional probability. There'll be other example videos that run through this sort of thing, but hopefully you found that useful and interesting, and I will therefore see you in the next video.